All right, we're going to talk about some effects that the forces that we encounter have on what we witness, on motion, on things in nature. So we'll review first. Let's talk about gravity. Once again, gravity is a force of attraction. Gravity pulls. Gravity, the law of universal gravitation, states that gravity is affected by the mass of objects and their distance from each other. On Earth, we talk about the acceleration due to gravity as being 9.8 meters per second, and kind of we talk about the force of gravity when we talk about potential energy. We talked about that force of gravity being that 9.8, so that's a good number to remember. So let's look at these. I know you've seen these before. Which pair has the greater gravitational pull? Obviously, it is this top pair because since they are all the same distance from each other, the two more massive objects will have a greater gravitational pull. And here, the two objects closest together, since they are all the same mass, the two objects closer together will have a greater gravitational pull. And between all these four, right, these are not very massive objects at all. So let's look at these more massive objects. And obviously the closer, more massive objects will be attracted more strongly with a greater gravitational force. All right, so let's talk about a concept we call free fall. Free fall is when the only force acting on an object is gravity, right? There would be no friction, there would be no fluid friction, no air resistance, nothing except for that force of gravity. That is called free fall. And a long time ago, Galileo Galilei, astronomer, scientist, discovered that all things fall at the same rate when there is no air resistance, regardless of their mass. And it was a great experiment. He did this from the Leaning Tower of Pisa. He had several similarly shaped objects, stones, of different masses, drop them from the tower, and they hit the ground at the same time. Therefore, if there's no difference in air resistance, then they're going to hit the ground at the same time. And it was kind of something he used to develop that concept of free fall. Objects that are in orbit, we consider these objects in free fall since gravity is the only force that is affecting them. That's why objects stay in orbit. Okay, like the moon in orbit around a planet. The moon is being attracted to that planet by gravity. The moon kind of wants to keep going in motion because of that concept of inertia, if you recall. Wants to keep going in motion because of the concept of inertia, but it's in a curved motion because of that gravitational force, but it doesn't slow down and stop because there's no fluid friction, there's no air resistance, there's no oppositional force. So the only force that's acting on that object is gravity, so we consider those objects to be in free fall. Without gravity, the moon would just keep going, right, off into space. But because of gravity, it stays in orbit around the planet. So, if all objects experience gravity because of their mass, right, then can something ever be weightless? Can something be weightless? Let's think about the concept of mass and weight. Think about what we talked about. We've talked about mass and weight several times. If all objects have mass, and all objects, because of their mass, must experience gravity, then can something ever be weightless? Well, what is weight? That concept states that weight is gravity's effect on an object's mass. So, no. Right? Objects are not weightless. Okay, when an object is what we call weightless, it is really in free fall. It's falling and just hasn't hit anything yet. So weightlessness is not really true if you examine the definitions of those concepts. Just doesn't have something for the force of gravity to pull it against. So talking about free fall again, right? The acceleration due to gravity for every second that you fall, as long as there is no resistance, then you accelerate at 9.8 meters per second squared. So after falling for 1 second, you will be going 9.8 meters per second. After falling for 2 seconds, you will be going at 19.6 meters per second. After falling for 3 seconds, it'll be 29.4, and after falling for 4 seconds, it will be 39.2. So you can see an object in free fall on the Earth accelerates 9.8 meters per second squared. So let's talk a little bit about that air resistance, that fluid friction again. Interesting concept if you think about it. In air, so if you have something that has air in it, or those objects are in air, you have a stone and you have a feather, and you drop them when there's air around, right? So obviously that stone is going to fall faster, right? Because the air, that air resistance, that fluid friction is pushing back on that stone, but it's pushing back on that feather even more because that feather has a wider surface area, and the friction affects that feather more. Therefore, the stone falls faster. However, in a vacuum, once again, an area with no air, that's what a vacuum is, then they're going to fall at the same speed because acceleration due to gravity affects all objects in the same way. 9.8 meters per second squared on the Earth. When there's no air resistance against that feather, then they are going to fall at the same rate. Back to the concept of free fall, because gravity is affecting all objects the same way, right? If you drop a ball straight down here, and if you kind of throw a ball off the side of the building, they're going to still fall at the same rate. Okay, they're going to hit the ground at the same time because gravity's pulling them down at the same rate, and they'll be affected by wind resistance, air resistance, that fluid friction at the same rate because it's the same ball. They're going to hit the ground at the same time, but obviously the one that you throw will hit the ground in a different place than the one that you drop straight, okay, because that acceleration due to gravity is the same. It's once again more about the concept of free fall. And if you throw a ball straight into the air, the air is going to slow it down. Air and gravity, right? Air and gravity are going to slow it down as you throw it into the air. And eventually, at some point, it's going to stop. And then it's going to begin coming back down. And because it takes the same amount of time to resist the force that you put into the ball as you throw it, then as it comes back down, it's going to be going the same speed and traveling with the same force as when you threw it, because it takes the same amount of oppositional force to stop it, and then that acceleration due to gravity will affect it in the same way. So when it passes you, it's going to be going at the same rate that you threw it. Think about it. And the concept of projectile motion. This is another concept, happens on the Earth because of gravity, right? If you throw something straight and you're on the Earth, then what forces are going to act upon that? Yes, there's two forces when you throw something on Earth. One of those forces is gravity. One of those forces is air resistance. Okay, projectile motion. When you throw an object, it takes a curved path because of those two forces, specifically because of gravity. That curved path because gravity is pulling it down. So when you throw something straight on the Earth because of gravity, it takes a curved path until it encounters the Earth, until it is pulled into the surface of the Earth by gravity. You got two parts of projectile motion. The horizontal motion, right? That has something to do with the force of you throwing it across. And the vertical motion, that's up and down, right? You might throw it up, but then eventually it's going to come down. And you might throw it straight, and it's still going to come down. That is the curved path because of gravity. So you have two parts of projectile motion. You have the horizontal motion because you apply a force that way, horizontally. And then you have that vertical motion because of gravity. Two parts. Once again, you throw that object. You can throw it upward. You can throw it at an angle. No matter what, it follows a curved path. It is projectile motion. That curved path is called a parabola. This shape is called a parabola. That curved path shape is called a parabola because of that combination of the vertical motion, up and down, and the horizontal motion. Parabolas you will learn about in math class. So let's see what we've learned here. Dropping something from a resting position, it's going to accelerate as it drops, right? Accelerates it on Earth, 9.8 meters per second squared. Gravity's pulling those objects down. Air resistance can affect the rate at which it falls, right? Air resistance is that fluid friction. If there's no air resistance, then there's not going to be that effect, and it will be precisely 9.8 meters per second squared. We have no air resistance, obviously, in a vacuum when there is no air. The concept of when gravity is the only force acting on an object, which cannot happen on Earth, once again, because there's air everywhere, unless you create a vacuum. That is called free fall. Orbiting objects, once again, in free fall because it's just that gravity. Let's think about Newton's laws, because Newton's laws help us to really understand all of these concepts. So Newton's three laws of motion help us to understand all of these concepts we've been talking about. So let's think about those three laws. Law number one, inertia. An object in motion will stay in motion, and an object at rest will stay at rest unless acted upon by an unbalanced force. Two, the acceleration of an object depends on the force applied to that object and the mass of that object. That seems kind of obvious. And three, for every action, there is an equal and opposite reaction. So in your notes, write down each of those three laws as I just described them, and then I want you to think of an example of how you encounter these laws acting in your world on a regular day. That is all.